Good evening, all. Now, session will be taken by Professor Priyanka Chawla, ma'am. So, let me introduce her. So, Dr. Priyanka Chawla is having a rich experience of industry and academia of more than 20 years. She is currently working as Associate Professor at the Department of CSE, NIT Warangal. Her major areas of interest include cloud and fog computing, artificial intelligence, evolutionary computing, and software engineering. She has published more than 80 research publications in referred journals, conferences, and book chapters. She has been conferred by several awards such as Research Excellence Award, Global Seminar Excellence Award, etc., by various renowned organizations. She is an editorial member and review committee member of various reputed international journals. Dr. Chawla has been associated with various institutes as member of board of studies and has worked as NBA and IQAC coordinator at various institutes. Dr. Chawla has delivered several invited talks in various conferences, FDPs, and workshops. She has organized several international conferences, seminars, technical events, and FDPs at various institutes. Dr. Chawla is a life member of ISTE and member of ACM and IEEE. So now I invite ma'am for this session.
Thank you, Navya, for your kind introduction.
Okay, ma'am.
Shall I start?
Yes, ma'am.
Yes, are you all able to see my slide? Yes, am I audible?
Yes. Yes, ma'am. You are audible, ma'am. And video is like PPT is also showing.
Okay. So we will be discussing about particle swarm optimization today. And this is the outline. First, we'll start with the introduction, like what is particle swarm optimization and its background. And we'll be discussing about optimization methods. What is optimization and optimization method? And then we will move to the particle swarm optimization, its origin, components. We'll be discussing the algorithm, and we will be taking a case study to study like how it works, and we'll be doing analysis of there. And I'll be taking two functions, objective function Rosenbrock and sphere function. So I'll be illustrating PSO using those example. And then we'll be discussing about the application of PSO, and we'll be discussing about advantages and disadvantages. So the very first, we will start with the very first thing is, what do you mean by optimization problem? Optimization problem. So what do you understand by optimization problem? And then what is the optimal solution? And the third is, what is optimal value? So if we talk about the optimization problem, we'll say it is a computational problem in which the objective is to find the best of all possible solution. And here we are going to find out whether the minimum value or the maximum value of the objective function in the search space. And when we talk about the optimal solution, we say it is a solution to an optimization problem which either minimizes or maximizes the objective function. That is optimal solution. And the third thing is optimal value. So optimal value can again be either minimum value or the maximum value of the objective function over a particular region of the optimization problem. So this is how we defined optimization problem, solution, and the optimal value. So let's take an example. Suppose this is a function y is f of x, and this is defined as sine of x plus sine x square plus sine x and cos x. So can you tell me how many global maximum, global minimum are there in this figure? Are you all able to see this chart? Am I audible? Yes, am I audible?
Yes, ma'am.
Okay, so can you tell me how many global maximum, global minimum are there in this graph? This graph is visible to you? So you can,
14 maximum.
huh?
14 maximum.
No, I'm asking about global maximum and global minimum. 14 maximum, like I'm not asking about local maximum. Global maximum and global minimum. So what is the optimization problem? Optimization problem is either to find the global maximum or global minimum. So how many, you tell me how many global maximum and global minimum are there?
1 and 1.
Yes, one and one. So can you identify those? Which one is the global?
There is
2.5.
2 point minus 2.5,
Yeah,
and the maxima is not very clear,
yeah,
but it is around again 2.4 or 2.5.
yeah. Correctly, very correct. So we have one global maximum and one global minimum. You can see here in the next. Are you able to see? This is the global maximum, and this one is the global minimum. Now, if I rephrase the question and I ask you like x-axis value is only varied from -4 to -4 to 6. So, will you be able to find out the global maximum in that case when the x varies from -4 to 6?
Yes.
But that would not be a global maximum. It will be a maximum. This point would be there. So that would be local maximum. So this is how we can differentiate. Like what is the like how local maximum and global maximum is different, because the main problem is to find the global maximum optimization problem. We need to find the global maximum. Should not fetch us the local maxima or local minima. So this is the optimization problem. So let's take one more example. Are you all able to see the another graph? So this is a plot of f of x and y, sine of x square plus sine y square plus sine x and sine y. So are you all able to see this? So this is somewhat complex. Okay, so what we have done here, we have added more variables. Now in this scenario, it will be very difficult to identify the global maxima and global minima. Okay, it is very difficult to point it out what where is the global maximum and minima. And mostly in real life scenarios we get these type of, we need to consider multiple variables, and we need to consider higher dimensional vector space. So in those scenarios becomes very difficult to find the global maximum and global minimum. So that is why we need a very good algorithm that should be able to find out the global maxima and minima. Okay. So let's see like how we can divide the optimization method. So we can divide roughly into classical methods are there, and then we have meta heuristics. So meta heuristic can again be divided into trajectory based algorithms and then population based algorithms. And then we have a nature, this population based algorithm, they are usually nature inspired. So, what do you mean by nature inspired? From which the algorithm has been designed with an inspiration of the nature, like evolutionary algorithms are there. You might have heard about genetic algorithms. Okay. And in the same way, we have a swarm intelligence. Like today, we'll be discussing about this particle swarm optimization. Other examples are ant colony optimization. So these are all optimization algorithm, and these are called meta heuristics. And then we have a bacterial foraging bee algorithm. So many algorithms are there. So why do we like why there is need to move to the optimization method? Like conventional, the conventional optimization methods are usually, they are called deterministic algorithms. So they have several limitations. So determinist algorithm means you will always be getting one output, and every time the output would be the same. But there are several limitations, like they always offer you the single base solutions, and they always converges to a local optima. Like in the previous example we discussed, our aim is to find the like global optima, not should not be the local optima. Okay, but these determinist algorithm, they usually they converge to a local optima, which is not the goal. So to overcome these limitations, so that's why several meta heuristics have come up to address the complex.
Madam,
Yes,
one question.
yes.
Uh, the global needs to be defined even in your first graph,
Hmm.
because the value of x is a continuous variable and the limit is infinity
Which graph you're talking
until the pattern repeats the first graph.
about? Hmm.
Until the pattern repeats, the if you set the limit on the theta or the x between a certain values, x here is in gradients. So
Hmm.
until you define that, you cannot talk about the global until the limits are defined. So in this, when you're talking about global, what is the what are the limiting factors is needs to be explained. I was not going to ask you, but now that we have come into the swarm method, I need to understand what are the limits. Now let's go back to that first graph.
So
Let
limits you have to define. Their search space has to be there, because
Yes.
infinity
Yeah.
cannot be you
See,
from the
this
infinity. We
this
cannot
this
be there.
yeah. If this graph, if I take from 100 or 300 to minus 300, you will find this pattern will repeat, because there will be a HCF happening somewhere,
Ah.
and that maxima will be there for each of those domains. So for that domain, when we define x here to here, then it will be the global definition, because the pattern need not repeat again.
Yeah, obviously we need to
Yeah, no,
confine the
it's
search
not
space.
obvious. It's
Yeah,
not
yeah.
obvious because
Hmm.
there is not one single global maxima until you define the limits. That is precisely what I was not going to talk about this, but now that we are going into the swarm, somewhere we need to understand what is the parameter x limitations.
So what is your question?
My question is, if I took x as minus 100 to 100,
Hmm.
then how many maximas will be there?
So for that you need a graph, na? Like if I talk about this graph.
Yes, ma'am. The
Yeah.
graph will be, there'll be several.
So yeah,
So,
yeah. It
ma'am,
has to
please,
be
please
defined
understand what
first.
I'm saying. Ma'am, please understand what I'm saying. You will be required to take a section of this graph, which is a repetition of the same pattern. Once the pattern is defined, then that is a complete global entity. Again, it is repeating, so we don't need that. So from x minus 36 to x plus 36, it is a complete graph, and that is the universe in definition. Then there will be one maxima and one minima. If they repeat, it is due to the property of the equation.
Yes, exactly. It is correct.
Yeah.
Whatever you are saying.
So my question comes here.
Hmm.
When you're talking about your um here, I would like to understand your definition of the universe.
Universe.
Yes, ma'am.
So let me complete. So let me
Yeah.
start with the particle swarm optimization.
Sure.
You'll be able to understand. Okay.
Yeah. Okay.
Yeah. So we were discussing about like this we optimization methods. This we have done. So meta heuristics we were discussing about. What is heuristic? Heuristic means it is a technique which aims to solve a problem faster when the traditional techniques are too slow. Whereas if we talk about meta heuristic, we say it is a higher level technique, okay, in which you will be able to get a sufficient good solution to the optimization problem. Okay, and we can divide the meta heuristics into two parts: population based and neighborhood based. Population based, you see, their evolutionary computation are there, and then swarm intelligence we seen from the that diagram also we seen. And then you see swarm intelligence, we discussed like ACO are there, PSO there. Then other algorithms are also there. Cuckoo search is there. Artificial bee colony algorithm is there. Then we have a firefly algorithm, bat algorithm, honeybee mating algorithm is there. Okay, so many algorithms are there which are like based upon swarm intelligence. And then we have a neighborhood based algorithm. So like simulated learning is there, taboo search is there. So they are all neighborhood based algorithms. So you can see, are you able to see this diagram? So this explains the particle swarm optimization like in the best way, like how it is inspired from the nature. So you see the left side of image, it gives you the view of, you see birds flying together. And the right side, it's you see the fishes, they search, you see they swim together to search for a food. Okay. And particle swarm optimization, it was proposed by James Kennedy and Russell Eberhart in 1995, and it is inspired by the social behavior of birds and fishes. And in this, it combines the self experience and the social experience. So they will not be working only based upon their own experience, but they will also get the information from their peers. Okay, like you can see, you might have seen the birds flying in the sky. So they not only adjust their position according to their experience, but they always also adjust according to their peer experience. In the same way, fish also, they search for food in the same pattern. So what is a particle? If we talk about particle swarm optimization, what do we mean by the word particle? So what is a particle? It represents a potential solution. Okay, each particle means a potential solution, and it moves in the search space according to its own velocity. So each particle would be having its own velocity, and that velocity would be combined with the self experience with the social experience. Self experience means like it will be having a memory. Okay, what was my previous experience, and then he compared with this position of the current position and compare whether it's better or not, and based on that, this is called self experience. Social experience, like based on the, you see, whole swarm is there, and from the experience of the swarm, the particle, they adjust, they modify their position. Okay, the optimization process continues until the swarm converges to either to a satisfactory solution or it reaches a stopping criteria. Okay, so we need to define some limit. Like she was saying, limit has to be defined. Without limit, we cannot find the, you see, the answer to a problem. So you can see here, so this PSO, it is designed to mimic the cooperative and exploratory behavior of swarms to search for the optimal solution in high dimensional search space. Okay, and it has been successfully applied to a wide range of optimization problem like function optimization, feature selection, clustering, engineering design and control system. And it has been widely adopted and developed in various, you see, fields for various research works. And various improvements also have been done to the basic algorithm. Okay, so again, you see, multi-objective optimization we can have, and then we can hybrid this PSO with the other algorithm, like we studied genetic algorithm. We can make a hybrid version of PSO with the other to solve the problems. And then why it is more very popular, particle swarm optimization, because of simplicity. It is very simple to understand and it is efficient, and at the same time it is very flexible if we compare to the traditional optimization algorithm. So you can see, are you able to see this? You see this figure on the right hand side, there is a red circle. So this is a vector. You see, this is the position, current position velocity of a particular particle. So is my slide visible? Yes, am I audible?
Yes, you're audible, ma'am.
Yeah, slide is visible.
Yes, it is visible.
Yes. So I was explaining this particle red colored circle, you see, and you can see this is the particle. Green denotes the particle best position. This is the best position, and this triangle denotes the global best position. And you see, it will not move according to its own experience, but it will be influenced by the cognitive means its own experience. This green colored square, and it will also be influenced by, you see, this orange colored rectangle, by, you see, social experience. So this is how it adjusts its new position. From here it will come here, it will not directly go here. So this is how it works. So let's see the components of particle swarm optimization. So it uses the number of particles we have. So what is particle? You can see here, if we talk about each and every bird, like in this picture, you see the pigeon is there. So many pigeons. So it is called a collection of, you see, so many birds are there. So each and every pigeon, you can say it is a particle. Okay, and you see so many birds, it will constitute a swarm. Okay, and you see they move around in the search space. A search space would be there, and they will look for the best solution. And what are the main component? The first important component is the particle. Like each and every bird, it's a particle. In the swarm, it represents a potential solution. So mathematically, we say it represents a potential solution to the optimization problem. And the velocity of each particle represents the direction and the magnitude of its movement in the solution space. And each particle in the search space, they will adjust its flying according to its own experience as well as the experience of the other particles. So you can see here, cognitive part is there and social part is there. Then another important component of PSO is fitness function. So what is fitness function? You can either call it a objective function. Okay, so fitness function is a scalar function that evaluates the quality of each and every solution. So how will you say whether this solution is giving you the best solution? You will evaluate the quality with the help of a fitness function. And what is the objective of PSO? It is objective of PS to find the particle with the highest fitness value. So the particle with having the highest fitness value would be considered as, you see, the best. You see, you can say this is the best solution. Okay, you can see the best and the optimal solution to the optimization problem. And again, the fitness function, it can either you want to minimize it or maximize it depending upon the optimization problem. So these three components, particle, velocity, and objective function, so they will work together, okay, in the swarm to find towards the optimal solution. And the optimization process continues until the swarm converges to a satisfactory solution or reaches a stopping criteria. Like you have defined, okay, this is my stopping number, some number of iterations you can define. Okay, I'm going to end by 100 iteration or 1000 iteration. Whatever solution I'll get, I will consider, from there only I'm going to consider the optimal solution. Okay, or you can say or the satisfactory, you are satisfied with the solution, whether it is a satisfactory fitness value or not. The final result, you see, it's the particle with the best fitness value, which represents the optimal solution to the optimization problem. So this is the basic algorithm of PSO. You can see here, what is the first step? We will initialize the swarm from the solution space. And in the second step, we are going to evaluate the fitness of each particle. And in the third step, we are going to update the individuals and global best. And then we will update the velocity and position of each particle. And fifth step is we will go to the step 2 and repeat until the termination condition is fulfilled. So this is the basic algorithm of PSO. And this is the flow chart for the same algorithm.
Ma'am, your slides are not moving, like you are stuck on slide 16.
Huh? Slides are not moving.
No, it's like 16, it's showing 16 number slide only.
Okay, wait.
The bird one.
Is it visible now?
Yes,
Madam.
now it is showing 19 number slide. Yeah.
So you,
The previous
yeah,
slide,
come to
for the,
19.
sorry,
Okay. So let me explain this.
after 16 number slide, now we missed.
Okay, you could not see.
Yeah.
Okay, no problem. I'll explain it. So this 16 slide is the components of particle swarm optimization. So there are three main components. The first component is the particle. Okay, particle means like each, and like here in this you see in this picture. So particle means each and every, you can say, okay, each and every particular bird can be considered as a particle in the swarm. Or you can say particle, you can say it is a potential solution to the optimization problem. Maybe this bird or this bird or this bird, you will give you a optimal solution to your problem. And second component is the velocity component. So velocity of each particle, it will be having, you see, the direction and the magnitude of its movement. Okay. And they will be the particle, they would be you see, they will be in the each particle in the search space, they will adjust its flying according to its own experience and the flying experience of their other particles whosoever are there in the swarm, and will be restricted, like certain limits would be there. And the third important component is the fitness function. So what is fitness function? This is a scalar function that evaluates the quality of each and every solution. So this would be the function which will tell you, okay, whether, how you're going to decide whether this bird has given you an optimal solution or not. You're going to evaluate by using some mathematical formula. So that is called this fitness function. And this the objective of particle swarm optimization is to find the particle which is having the highest fitness value. Suppose there are five particles, and the first particle gives the, you see, the value to the fitness function gives the value 6, and the second gives 5, and the third one gives 4, and the fourth one gives maybe 1, and the fifth one gives maybe 3. So the highest, if it is you want to maximize it, that again you have to decide whether you want to maximize the objective function or minimize it. If you want to maximize, then it would be 6 particle, the one with having the 6 value would be considered the best. If you're going to minimize it, then the particle having the value 1 would be the best. Okay, so the fitness function can either be, you can define it whether you want to minimize it or maximize it, and depends upon the type of the problem that you want to solve. Okay, clear? So now this algorithm, this will optimization process will continue until the swarm converges to some satisfactory solution, or it reaches a stopping criteria, such as maximum number of iterations you have reached. Or you say, you can say, okay, only 100 iterations I want to, whatever solution I'll get, I will be happy with that. So you're going to put a limit on that. Or you can say you satisfactory, some may not be the best solution, but you get some satisfactory fitness value, and you say, okay, this is fine with me. Okay, and the final result is the particle with the best fitness value, which represents the optimal solution to the problem. So this is the algorithm, basic algorithm. So there are 5 steps in this. The first step is, first we have to initialize the swarm from the solution space. Okay, and then evaluate the fitness of each and every particle. Third is you going to update the individual and the global best. Global best means the best value among all the particle in the swarm. Fourth is update velocity and position of each particle. So you're going to, so there will be 2 updates you need to do in this algorithm: velocity update and the position update. First, you will find out the velocity update, and based on that, you're going to find the position update of each and every particle. Fifth is you need to go to the step 2 until the termination condition is satisfied. Okay, so either you can fix, or you are satisfied with the satisfactory result. So this is the flow chart for the same algorithm. Now let's see how do we define it mathematically. Swarm. So if we talk about a swarm, what is a swarm? It is a set of particles. Okay. And what is a particle? A particle is a potential solution. And this particle would be having two things with it associated with. The first one is the position, and the second is velocity of a particle and position of a particle. And if I represent a position with, you see, xi, okay, it may have like, you can see it all belongs to, we can define it mathematically. In the same way velocity has been defined, okay, with different velocity components, and each particle maintains its individual best position that we call particle best. Like suppose in the iteration 1, the particle value best, you see its current value is 5, and in the iteration 2 its value is 6, okay, and in the iteration 3 the value is 7. So if it is maximum, you see you're going to your objective function is to find the maximum value, then the seventh value would be considered as the best fitness value. So you, that would be the individual best position, particle best. And then other thing is the swarms, the all particles will maintain its global best. So particle best would be, you see, for each and every particle there would be a, suppose there are 100 particles, then there would be 100 p best values. And for a swarm, for whole swarm there would be only one global best. Like if there are 100 particle there would only be one global best, but if there are 100 particle there would be 100 particle best. For each and every particle there would be particle best, and global best obviously would be 1. Okay. So these are the equations, you see the algorithm it's going to use. So you can see here velocity, it consists of three components: inertia, cognitive, and social. Okay. So you can see here in the inertia component, you can see then inertia means, so we'll be discussing this in detail. So let's see just the formula. So what is this? W into vi of k. Vi k plus 1 means the next, what would be the next velocity depends upon the initial velocity, and this w is the constant value, plus c1, again this is the constant value, into some random value. This random one is some random variable, and you can see here it is multiplied with the difference between particle best and the you see the particle's current position. So that is called cognitive, the difference between particle best value and the current value, plus c2. C2 is again a constant, and this random 2 is the random variable. And here again it is multiplied with the difference between global best and the current position. Okay. So this is called social factor. Second component is called cognitive, based upon its own you see intelligence, and the third one is based upon the social intelligence, okay, by like the experience of all this one. Okay. So these are three components: inertia plus cognitive plus social. And this position update is based upon the velocity update. So how we find xi k plus 1 is xi of k, the initial position, this new position would be based upon the initial position plus the value, the velocity value at the new position, vi k plus 1. So these equation updates you need to do in PSO. So let's understand this with the help of a small problem. Suppose xk, it has been defined, the current solution is at 4, 2. Okay, x value of x is 4 and y is 2. You can see xk is here, current solution point. And here this blue one, it's particle best position. So it has also been given to you. Suppose it is x value is 9 and y is 1. And then we have a global best. Global best is also given. So it is represented by a red dot here. And the value has been given, x is 5 and the y is 10. Okay. Now we have to do the solution update. Means we need to find out the new, what would be the new position based upon these values. And suppose the inertia Vk has been given as -2 to 2. Okay. So we just need to put in this equation and we can find the values. So how we can find out? So you can see first we need to, inertia is already given to us, -2 into 2. Sorry, -2 and 2. And the cognitive part would be the difference between particle best and the current position. The particle best was also given 9 comma 1, and the current position was also given 4 2. So you just apply simple mathematics. 9 minus 4 is 5, and then 1 minus 2 is minus 1. So this is the position best, okay? Or you say the cognitive part. We got the cognitive part of the velocity equation. And then the social part. So this is the difference between global best and the current position. So you just you see 5 minus 4 will come out to be 1, and 10 minus 2 will come out to be 8. Okay. So this is our you see the social part. So we just we need to put in that equation vk plus 1. Inertia was given to us minus 2 comma 2, and then this 0.8 is given to us, the value, the c1. And we just put this particle best here plus 0.2 here, and then we put the global best here. So we get the new velocity position. What is the new velocity value? 2.2 to 2.8. Okay, is it clear?
No, ma'am. Please explain it again.
Okay. So in the question itself, it is given the current position. Current position means xk, the value, what is xy values have been given, 4 comma 2. Okay, it is given to us. And particle best, it's denoted by blue. You see, just I'm just want to explain you like how the velocity updates are done. Particle best value, suppose it is also given 9 comma 1, and global best is also given 5 comma 10. And what you have to do, like in here we have discussed now, the vik plus 1 is equal to this inertia, how we find out the velocity, inertia plus cognitive plus social. Okay, so this we need to find out. This we already have. And inertia is also given to us because vk plus 1 is inertia plus cognitive plus social. So minus 2 comma 2 is also given to us. Current solution is also given. So we simply put, you see, we will first, inertia is given to us. Cognitive part means how we define the cognitive, the difference between the particle best position and the current position. Particle best position is given to us, you see 9 comma 1. So we have put it here 9 comma 1. And this current solution value is also given to us, that is 4 comma 2. So we have just put it there. So we got 9 minus, so we just subtract x value from the x value. 9 minus 4 is 5, and 1 minus 2 is minus 1. Is it clear, this cognitive part, how we have
Yes,
done?
ma'am. Yes, ma'am.
And in the same way, we will calculate the social component also. What is the formula? The difference between the global best and the current position. Global best value is also given to us, that is 5 comma 10. Okay, so you just subtract this x component from the x. 5 minus 4 is 1, and then y component from the y component. 10 minus 2 is 8. So this is the global, we got this social component and cognitive component. Okay, so velocity update is just the summation of inertia, cognitive part, and the social part. So inertia was already given to us minus 2 2, and here 0.8 we have, you see it's the constant value it is given. Okay, 0.8. And here you computed this cognitive part, 5 comma minus 1. This also 0.2 it is given to you. Okay, and 1 comma 8, this is the difference between the global best and the current position, that is 1 comma 8. And if you do simple addition and subtraction, you will get this 2.2 comma 2.8. So this is the vk plus 1 velocity update. So this is how we find out the velocity update. Is it clear now?
Yeah, ma'am. Yes.
Okay. So after the velocity update, what is the next part? We need to find out the position update also. Okay, so velocity we already computed. So what is the formula for position update? Xk plus 1 is the current position of xk plus vk plus 1. So this was given to us, current value, value 4 2. And you just put this value vk plus 1 over here. This we just computed. Okay, so just add the x component with the x component. 4 plus 2.2, it's 6.2. And then y component with the y component, you see 2 plus 2.8, 4.8. Okay, so this is our new, you see the x position, new position update value. Is it clear how we got this? Based upon the velocity update only, we got this position update. Clear?
Yes, ma'am.
So here we can just see the movement is towards a promising area to get the global optimum value. Okay, and each particle adjusts its traveling velocity dynamically according to the flying experience, its own experience, that is cognitive part, plus the social experience, means the experience of its colleagues. Okay, and each particle, it tries to keep track of the personal best value, and personal best value would be different for each and every particle, and global best value would be one for the, you see, the swarm. And each particle modifies its position according to the current position and the current velocity, and the distance between the current position and the particle best, and the distance between the current position and the global best. So this we did, we did in the in some, in the previous problem. So let's take another example. So now here the objective function you can see here. So this is f of xy. So little bit complicated objective function. Okay, so we'll follow that basic PSO only. So we will create a population of particles which would be uniformly distributed over x. Okay, and in this we will evaluate each particle position considering the objective function. Now, objective function has been given to us, f of xy is this: x minus 3.14 whole square plus 5 y minus 2.72 whole square plus sine 3x plus 1.41 plus sine 4y minus 1.73. So this is our, you see, the objective function or fitness function. Third step is, if a particle's present position is better than the previous best position, then we update it. Okay, like if we get the better value, objective function of a new value is better than the previous value, then we are going to update the best value and find the best particle according to the particle's last best places. So we will find the best particle and then we'll update the particle velocity. So with the same formula like we did in the last example, inertia plus this cognitive plus social, and move particles to the new position with the same formula like xt is equal to previous position and plus the this new velocity value. And seventh step is we'll go to the step 2 until a stopping criteria is satisfied. So you can see here, so this function, it is very hard for to find out its minima, because a local minimum found is not necessarily the local minima. It's very difficult to find out. So these kind of problem we just apply. So that is why we apply optimization methods. So this is our, this function looks like a curved egg pattern. Okay, so we just plot a, you see, contour plot of two-dimensional plot I've drawn here. Okay, and I've given some range have been given in this region. I've specified the region. X is greater than equal to 0 and y is less than equal to 5. So this region has been specified. From here only we need to find out the, you see, the global maximum optimum values. So you can see here, this is the initial position of the particles. You can see here. So we have created 20 particles, okay, at random locations in the region. As all these blue dots, these are particles. And in total, we have created 20 particles. And here you can see this position of global best is marked with the star. This is the global best. I've marked with the star icon. And then let's suppose that C1, C2 is equal to 0.1 and W value is given to be 0.8. And we just, we will apply the same formula like we did in the previous example, and we'll find the update in the position and velocity. Okay. and then we'll update the particle best and global best, depending upon like whether the new you see the position is better, the fitness value of a new vector is better than the previous one, then that we will update the particle best. In the same way we'll update the global best also, and we'll mark the best position of each particle with the black dot. You can see these black dots, so they are all, you see, the best position of each and every particle. Then you can see this is a position update. You see after two iterations, these are the position updates, and these are the position of particles after 5 iterations. So you can see it is converging after 5 iteration. You can observe it started to converge, and this is the position of particles after 20 iterations. Okay, so they have converged, they have found the global value. And you can see here, you can just see in this animation, so it's just a resemblance to the movement of a flock of birds. So in the evening time or in the morning time, you just see the birds, they fly together. Okay, so from this animation, you can see like iteration number, it's increasing and they converging. Okay, iteration 41, 44. Okay, so this is the animation you can see. Is it visible, this animation?
Yes, ma'am.
Yes, it is beautiful.
Yeah. So this is how it finds the solution. So let's do the analysis of this velocity update only. You can see here. So this Vt plus 1, you can see here the first component is called, it's responsible for the diversification. Okay, so we say diversification means it searches new solution and finds the region with the potentially best solution. So it consists of two parts. We also call it inertia. Like in the last example I mentioned, and this is the inertia value, it is already given to you. So inertia value, it makes the particle move in the same direction and with the same velocity. And what is the meaning of W here? You see the parameter W is the inertia weight, and it is the positive constant. And this parameter is important to balancing the global research in two ways: exploration and the exploitation. Exploration, if when the exploration would be high, when you set the higher value of W, so it will explore more. Explore more means it will diversify, it will explore in the more space. Such space would be more, it will explore more solution. And exploitation would, it's called the local search. It would be like focused on morely on particular you see particular area, that is a local search, and it is also called as exploitation. So whenever you set the value of W lower values, then it tends to exploit it. It means it will be more towards the local search. And when you set this value of W more value, then it would be more explorative, so more exploration would be there. So this is the you see this component would decide the diversification, whether you want to explore it or you want to exploit. The second and third components, they are more towards the intensification. So it explores the previous solution, find the best solution of a given region. So the second component is more, you see, it's towards the personal influence. Okay, it improves the individual, makes the, you see, we find the difference between the particle best and the current position. So it improves the individual, make the particle return to a previous position if it is better than the current one. So this is, you see, we also call it cognitive, or we say personal influence. Why? Because we are only finding the difference between particle best and the current position. And the third component is the social influence. So here we find the difference between the global best and the current position value. So it makes the particle follow the best neighbor direction. Whosoever a particle is giving the best value, each and every particle would be like, they will follow that particle more. So that is social influence. So let's see, like if we set the value of W equal to 1, so then particle motion is entirely influenced by the previous motion. Okay, and this particle may keep going in the same direction. So it's very important to carefully design the value of these constants. If you set it to 1, so it means it will keep going in the same direction. On the other hand, if you just you see, if you keep it less than 1 and greater than equal to 0, such influence would be reduced. That is why it is usually kept less than 1, because you don't want to make the particle move in the same direction without any influence. Okay, so particle will go to the other regions in the, because you want the particle to move in the other region in the search domain. Then another parameter is C1. So this is individual cognition parameter. So it weighs the importance of the particles on previous experience. Okay, so if you put a value more, it means it is giving its more importance to the its own particles own experiences. Okay, and the other hyperparameter is that that the second term, that is random variable. So this random value parameter, it is usually in the range of 0 to 1, and this random parameter, it plays an essential role in avoiding the premature convergence, increasing the most likely global optima. So it helps you. It's you see, it plays a very important role in avoiding the premature convergence. Okay, like it should not end up finding the local maximum or local minimum value. Okay, C2 again is the social learning parameter, the third one, and it weighs the importance of the global learning of the swarm. So if you give this value more, it means you want to give more importance to the social learning. And this another random variable, it has the same role as that of you see U1T. So let's see, you see, if there is a case when we set C1 equal to C2 equal to 0, if we set the value C1, C2 equal to 0, so all particles will continue flying in their current speed until they hit the search space boundary. Like here, C1, C2, let's see that. You see equation again. So if we put this C1, C2, 0, it will be 0. Whatever the value would be, will become 0. So it means it is only affected by this W inertia. Okay. So it will be in that won't be the UC won't be. So it will just current. It will just move in the current speed until they hit some boundary. Okay, and in case when C1 is greater than 0 and C2 is equal to 0, means you want to make the social influence part as 0 and you want to make the particles independent. In those cases, you put the value of C1 greater than 0 and the C2 equal to 0. Okay, and if you want like they should be, in another case when C2 is greater than 0, okay, and C1 is 0, it means it should not be affected by their own experience. They should be attracted towards the experiences of entire swarm. Then you can set this value. And
Can the random number be 0? UT?
pardon?
The random number UT, can
Uh,
that be 0?
so we just discussed now, it's in this range.
Yeah, 0 to 1.
One,
So
yeah.
0 is included in the value
Yeah,
set.
yeah, yeah.
In that case, it will be a 0 value again.
It can be 0. It depends upon you what values hyperparameter you want to set.
Okay.
Again, depends upon the problem type, no? So generally we do not set it 0. Otherwise we won't be able to find, you see, the optimized solution.
No, I asked because it is a random number.
Yeah. It can
That
be
is
0.
why.
Yeah. Now next is, in case if C1 is equal to C2, they are all non-zero, okay, not 0. All particles would be attracted towards the average of particle best and global best. So this is always we will look for, like they shouldn't, particles should not only influenced by its own experience, but should also get the experiences of the best other particles also, their colleagues. So this is, you see, this is another example, Rosenbrock function. So this here we want to minimize the function. The objective function is to minimize it. Okay. And this objective function has been given 100 xi plus 1 minus xi square and this is whole square plus 1 minus xi whole square, and the bounds have been given. You see the xi is greater than equal to minus 5 and less than equal to 5. Okay, for I is equal to 1 to n. So this for this again like we did for the earlier example, so the same way for this also we can do. You can see now I've taken the population size to 8. Population size n equal to 8 means there are 8 particles, and the value of t I have taken 1. So you see these value initial positions have been given. This is the, you see the table. So this index in the first column I have plotted the index 1 to 8 means first for the value of this part position value, and this is the velocity value. Second column is the position value, and the third column is the velocity value. And for each and every particle initial position has been given, and this velocity is given 0 in the initial, 0 in the first initialization stage it has been given, because we need to find it out. So these values, suppose they have been, it has been given to you. Okay, so the same thing we are going to do, like we are going to find out the position update and the velocity updates. Okay, and the population size now we have taken to 8. And you see the objective function is also given to us, like Rosenbrock we just explained. Okay, and you see the position value for the first particle. You see this is the position value. We will evaluate its fitness. How we evaluate? Based upon this x and y value. Okay, so you just put this values over here in this function. So the f of this particle first position would come out to be 357.154. So nothing I've done, I've just put this value for the first particle. I put this value here in the function. So I got the objective, the fitness value of the first particle. In the same way, for the second particle, I've evaluated the fitness value of the second particle. Okay, so how we are, why we are evaluating this fitness value? Because based on the fitness value only we are going to decide now which, like in the second iteration we have to decide now which particle is the best one. So it is decided based upon the fitness value. So this is the first iteration. You see in the first round we just we calculated the fitness value for each and every particle. Is it clear?
Yes, ma'am.
So in the same way, this value we got this for each and every particle. The fitness value has been evaluated simply by putting in this fitness function value of x and y. And you see here, this is the first generation. So you can see here, this is the particle 1 position and the fitness value of the first particle here by using that fitness function. And since this is the first generation, so the local best would be the particle itself. So this is the particle best because it's the first iteration. It has nothing to compare with. So we'll take it, all are same. Particle best values all are same as that of your current position. You can see. So that is why column number second is same as that of column number 4. Okay. Is it clear? Particle best in the first generation, why the value of column first second is same as that of column 4. That particle position is same as that of particle best. And for the same, you see we can find the global best also. You can see this these you see 8 particles are there, position there, fitness function is there. This is the local best value which is same as that of the current position. So how we are going to find out the global best? Global best will be decided by the fitness value. You can see the fourth particle. What is the fitness value of the fourth particle? You see it is 167.414. So it is minimum of all the values. Okay, so it means if it is the the objective is to minimize the objective function. So if this is the minimum value, it means the position value of this particle would be considered as the global best. So here I put, like I told you now, for whole swarm means for all particle the global best value would be same. So that would be minus 0.639 comma 1.692. Is it clear how we got this global best value? In the same way, for each for all particle, the global best value we have just put in this fifth column. Yes, am I audible? Yes, is it clear? Am I audible, guys?
Yes, ma'am.
Okay. Now the next step is that we have found that global best and particle best. Now we need to find out the velocity update. Again, the velocity update, there would be three components. This we velocity update, how we calculate, we already did in the previous example. So it has three components: inertia, and then we have the cognitive part and the social part. And here we are going to assume the value of W is 0.75 and C1 1.5 and C2 is 2. And this, you see the random numbers have been given for, you see for each and every particle random number has been given. So in the form of tabular form it has been given. For particle 1, the U1 random variable is 0.661 and U2 is 0.312. In the same way, for the second, the random variable, all random variables have been given in the tabular form. So for the particle 1, you see this was given to us, the initial position 2.212 and 3.09. In this table it was given, you see, from here we took this value, and this initial velocity was zero. This I shown you, like we assume that initial velocity we are taking it zero. Okay, then you see here we have just put those values, and then you see we need to find out local best was also same, because the first iteration the local best is same as that of the current value. And global best we found that value, you see, minus 0.639 and comma 1.692. This is our global best, okay, based upon the fitness value of you see each and every particle fitness value we computed, and the one which having the lowest value for the fitness function, you see the position vector has been noted, that is the global best value. And this u1 has been given to us in this table 0.661, and u2 value has been given here 0.32, and we just apply the velocity update here. You see here, what I've done, I am computing the x component separately and y component separately. This is for the x component. So I will just apply this inertia weight. I will apply 0.75. It is given to us. Initial velocity is 0. Okay, so it has multiplied with 0 plus this C1 I've taken from here 1.5, and then multiply with the, you see the x component I am computing. So you just this random value multiply with the random, first random value is given 0.661, and this difference between the particle best and the current position, the particle best and current position value, it's the same. So this you see the whole will become 0, plus this you see the social component. So this C2 value has been given 2, and you see this 0.3.12 has been given from this random variable. Okay, and you see here then you again multiply, you see the just subtraction between the global best and the current position. The global best value is minus 0.639 minus 2.212, so it will come out to be minus 1.779. So this is only the x component. In the same way, the another one you can compute similar way, 0.75 into 0 plus 1.5 into 0.661, and then you just this y component 3.009 minus 3, because particle best and the current position value they are same. Okay, plus 2.0 we have taken from here this C2 value, and this U2 value is given here 0.312, and the difference, you see the global best 1.692 minus 3.009. So we got this value minus 0.822. Is it clear how we find this velocity update? Is it clear? Yes, am I audible? Yes, are you able to hear me?
Yes, ma'am.
Yes, okay. You understood this concept, Mamta?
Yes, ma'am.
Okay. Now, in the same, you see, for the particle 2, for each and every particle, we need to find out the same way we would be applying. Like for the particle 2, this was the current position has been given and velocity is 0. Okay. And local best is same because it's the first generation. Global best would be the same for each and every particle. Okay, u1 and u2 value has been given, and this velocity update for for you see the x and y we have computed in the same way like we did for the first particle. And this way if we go, so we will get the velocity for each and every particle. You see x, first column set the x component and the y component for each and every particle. So we got this. So you can see here, this we have done for each and every particle. Velocity update we have found. Okay. Now the next step is to find the position update. So position update is dependent upon the velocity. Okay. So that is why we computed the velocity for each and every particle. In this column, these are the velocity updates. So you see here, we will just put the values. New position value would be the current position value plus the velocity that we found in the previous. So this was, you see, you can see the particle. So here we have put we have put the limit minus 5 to 5. So therefore you see you see the one value position, we got this value position update. You know how we got this initial position plus velocity from this figure. We just did some simple addition and we got all this value. For each and every particle, position update has been given for this t is equal to 2 for the second generation. And but you see for the third particle, the second this value has been come, this y component value is coming out to be 5.893. Now in the when we were discussing the initial slide, I gave you a bound now, so that bound on this x2 is minus 5 to 5. Okay, so therefore we keep a position vector for solution 3. We need to keep the bound, so this will give, we'll just put a bound and we will make it 5.0. Okay, why? Because we just convert 5.893 to 5.00 because the bound was given. Clear? And then we will the next step is we are going to again compute the fitness of all this new position values. So we are going to compute. So why we are computing the fitness value? Because new position value has been given, we have generated for t equal to 2. Okay, and fitness will compute again. We apply the same formula, the fitness function that we discussed earlier. So we just put this value x and y and we will find out the fitness value. Okay, and based upon that you're going to decide, okay, which whether you want to, now you can, now we have two generation, now you can decide based upon the fitness value. You just compare the fitness value of new position value with the fitness value of the earlier position value. So the, if it is minimize function, then the value which is having the less fitness value, you're going to select that. Okay, so in this way you are going to select the fitness which would be the particle best position. So now again this for the iteration 2, so this value we got 0.4332.187. So we just kept it over here, and the velocity also we get. Okay, we just computed earlier. Now the local best here you see. Now you see the in the previous iteration for this particle number 1, so the fitness value was 357.1.53, and in the new iteration you see the value fitness function value is 399.9284. Now which one is the lesser one? So according to that we are going to decide the particle best. So here you see 399.984. So it is giving more fitness function value is giving more, but our aim is to find the minimum value. So that is why we say the local best of the particle, it's the previous position. So we, what would be the particle best value? It would be the previous position. So we will not put any update. So this is the new position. So we will not put update. It will be the same. And this u1 and u2 value, it is you see we have taken from this table. And for finding the global best, how we can find the global best? So we are going to analyze all the values, fitness value for each and every particle. So you see, we find out the minimum one. Which one is the minimum? You can see 153.484. Okay, so this is the minimum value. And what is the position value for that particular minimum value? That is minus 0.590 comma 1.577. So this is the global best. You got how we got the particle best and global best value? Yes, Mamta, is it clear how we got the
Yes,
global?
ma'am.
Yeah. So here you can see here. So in this table, I've just put it. You see 357 value is less than 399. So particle best would be the previous position. Now here this you can see this for the second particle, the fitness value of the second iteration is lesser one. So we are going the particle best for the this would be the new position update, new position vector. In the same way we have computed like all green, those who have marked green, that means these are the better fitness value, and that is why we have updated the particle best. Only for the first particle we have kept the previous position. For all other particle we have updated this position values, position best values, depending upon the fitness value. So this velocity update we did just for the second generation velocity update. With the same procedure we updated the velocity of each particle. And you see here, you see particle best, sorry, particle current position and the velocity. So by applying the same position and the velocity update, we computed this value. And again, you can see particle 3, 6 and 8, they are coming out of bound because we were given, the bound was given minus 5 to 5. So you can see in the particle 3, the second component is coming out to be 9.827, the new position, position at iteration 3. So we have to put a limit of 5 here. 9.87 would be converted to 5. And again, you see particle 6, the y component is 5.793. Again, we have to put a limit here because it's more than 5. So we have to make it within the boundary.
What,
Okay.
madam, I would like to interrupt. What exactly is happening to these particles in the real world? Suppose these are 12, 8 birds who are flying, and
Hmm.
the bird transgressed due to maybe the cognitive or its personal influence or the global influence, little haywire to 9.8. But
Hmm.
then when if you're putting it back to 5, in
Hmm.
physical world he's already gone astray. It's uh, like a hoop, you're moving the string with something on the side, because it has its velocity and it has its direction,
Hmm.
and it has gone out. So if you correct it'll, I'm not sure if it'll be corrected properly. So can you please throw some light on this, what exactly is happening when I
So
want to
we,
imagine in physical world?
like in the physical world, like suppose if we can take a very simple example, like they want to search for a food in a particular city, like if some bird is trying to go out of the limits of one city, so it is always discouraged because they need to they need to be in certain area, no? So that is why we are putting a bound here. That is why
No,
9.827 we just we put a bound. Okay, they in this weather they're going to stay in this city only, so they should not search for food in the another city. So
okay,
this way
ma'am.
you can relate.
But these outliers will be only few, right?
Yeah, only few would be there.
But if half the swarm gets values above 5, then
uh,
we should drop that experiment altogether.
then you yes, you need to not drop the whole experiment, but you can increase the iterations. Iteration numbers can be increased. so that you can like velocity update every time you're going to do. Now you're going to put a limit, then velocity update, then the position iteration numbers can be increased.
Okay. Okay. Thank you.
So you can see in the similar way, particle 6, we just put the, you see 5.793, we put in the bound. And in the particle 8 also, like X component was coming more than 5. So we just put a limit. Okay. So this would be the updated one. You can see here, we have changed the third particle for the sixth particle and for the eighth particle. So we just changed, like for the third, the y component was out of bound, and sixth component again the y component was out of bound. We changed to 5, and for the eighth also x component was out of bound. Okay, and again for this at the third iteration, you see the this we are computing the fitness value. So you see for each and every particle, the fitness value, you see the green one I've highlighted means this would be the global best value now for the next iteration. Okay, and you see here again position. Now you want to compute. Why I put it here? We need to compare compute the particle best value also. Particle best value would be compared with the previous fitness value and the new fitness value, and we were taking the minimum value. So based on that, we are going to fix the values. So in the same way, we'll compute like we did for the first and second iteration. We will just move like this. Is it clear? So this is how you see why I have given you this problem to understand how the PSO velocity updates, they work with different iterations, how they compute the values. Okay. Now let's see like the application of particle swarm optimization where you can apply these algorithm. Like if you want to optimize the functions, okay, like you have a single objective function or a multi-objective function. So function optimization if you want to do, and you want to find the global minimum or maximum value, then PSO is the best you see optimization, because it's very simple and easy to understand, and you can apply it. And in the machine learning also you can use PSO, where you can use it to optimize the parameters of machine learning. Like, you know, if you have worked in the machine learning algorithm, so it is very difficult to identify the best parameters. What would be the best? Because the value of parameters only would define whether you're going to get a better trained model or not. So you can optimize the parameters of machine learning algorithms by using PSO. Like if you want to use artificial neural network or sport vector machine and you are not sure which parameter value you should take, so you can optimize, you can make a use of PSO to optimize the parameter. And then in signal processing, PSO you can use to optimize the parameter of signal processing algorithms, such as filters, equalizers, and this channel estimators. Those are from, you see, electrical or electronics field. They would be able to signal processing. If you want to do there also, you can apply PSO. And this control system like robotic system or aircraft control system and power system, so there also you can use PSO to optimize the control parameters of those systems. And in the data mining also you can use PSO to optimize the parameters of data mining algorithm. Like clustering algorithms are there, feature selection, association, rule mining for the optimization of parameters. And image processing, if you're working in the image processing, then also you can use PSO to optimize the parameter of image processing algorithm. Like you're using some image compression or image enhancement and image segmentation. So there you can make a use of this particle swarm optimization. And what are the advantages? Like it's very simple. You have seen like it's very simple mathematics we need to do: addition and subtraction, velocity update, and then position update. So it's very simple to understand. Okay, and flexible. It is you can handle the problems with different dimensions and types. Like you can either work in the same. If you have a single objective problem, then also you can use PSO. If you have a multi-objective problem, in that case also you can use PSO. And if the continuous and discrete problems, both type of problems, you can make a use of PSO. For the linear and non-linear problems, it's very flexible, any kind of problem you can apply. Then is global optimization, like so it's the global optimization algorithm that can find the near optimal solution for problems with multiple local optima. Okay, computational efficient, it's very computational efficient. Okay, like very low computation cost per iteration, because only simple computation need to be done. So let's see what are the disadvantages of PSO. It is very sensitive, you see, to the parameters. So like if you make a change to the inertia weight altogether, we discuss the value of inertia weight W, and then C1, C2. Based on those value only, you will be able to find the optimal value. Depends upon the value of parameters that you are going to choose. So it's very sensitive to the parameter values, and like which may affect the performance of the algorithm. And the second advantage is the disadvantage is the convergence speed. So it may converge slowly in some cases. Okay, like the problem with complex solution spaces. So the convergence speed is like bit slow.
Uh,
So yeah.
Ma'am, one question.
Hmm.
We had the local influence and the global influence.
Yes.
In PSO, are there any other influences like gravitational influence, or can some more influences be put in? Or the PSO is simply inertia, personal influence, and social influence?
So only three components are there, and they have defined
Okay,
three components: inertia, and then social influence, and then the you see the personal influence.
okay.
Yeah.
No modified
Yeah,
influences.
modification you can always do. Like you can define your own algorithm by doing modifications. So like in like hybrid algorithm, you can just mix the genetic algorithm with the PSO. But the basic PSO, it works like this only. You can make a change to the equations, and you can say, oh, this is the new algorithm that you can name as yours algorithm, Madhavi algorithm. You can name it.
Ma'am, one more question comes to my mind is,
Yes.
before you start any sequencing, the few things that you should know is initial inertia, which
Yes.
may also be done by trial and error for a swarm or for a given problem. Another thing would be the random variables,
Yes. Yes.
correct?
Uh,
That is decided randomly. What else? But initial position.
Initial position we just discussed. Now its velocity is there, initial position, its current position is there, and the hyperparameter values are there, and the weight, inertia weight is there.
Okay,
Basic PSO, other things are not there.
okay,
Yeah.
okay. Thank you. Very beautifully explained. Thank
Yeah.
you so much.
Most welcome. Yes, any question? Do you have any question? Any other question? So now we will see, like, see this algorithm we have seen. Okay. No, I would like you to like how to do the coding part, like in the MATLAB, like if you want to do. So I'll be sharing one problem in the MATLAB with you all. Like, do you have a count? Do you have access to MATLAB? Like you work, if you work in MATLAB, then it's very easy for you to understand. I will be explaining one problem in MATLAB. Yes, any questions, Smita?
Hello.
Sunita?
Ma'am, besides MATLAB, which other softwares can work for the PSO?
Huh?
Besides MATLAB,
Huh.
in which other softwares can we do this
Yeah,
algorithm or
any
coding?
like you see algorithm, na, any programming language, whichever you feel comfortable, Java or Python, you can code it just like
Okay.
other algorithms you code, na? Same way.
Okay. Okay.
Yeah.
Okay, ma'am.
So any other question, or shall we start with the implementation? One simple problem I would like. you to see like in MATLAB how we can do.
Yes, ma'am. Please go ahead.
Yes.
Ma'am, we can start with the MATLAB.
Huh? MATLAB, na? Okay.
Yeah, yes, yes.
Yeah, let me share. So are you able to see my screen, the MATLAB?
Yes, ma'am.
Yes. So you can see here I am using this online version of MATLAB. If you have a account, then it's very easy. Otherwise, it's very simple to use MATLAB. Have you worked in MATLAB? So you don't need to install. Like you can just this online version. You can the free version is there. You just type online MATLAB. So this link will come. You just click on that link, and here you can see you can register for the education purpose. You can select the education part, okay, and then you select the academic and this get a free trial. There is option of get a free trial. You just click on there. Okay, so if you click on that, it will open the, like here I am already registered, so it will open my this MATLAB directly. But for you, it may not open directly if you don't have account. It will ask you to create the account. So you just register yourself over there, and you can use the you see the MATLAB online. You can use here. You see the option open MATLAB online. Can you see this? This option is there, open MATLAB online. So you just
Yes,
click
yes.
on this tab. Once you register, you'll be able to see, and then you can start working. Like this type of screen will appear. Okay, so I've written a simple PSO. The same algorithm I have implemented here in the MATLAB. So you can see here, see if you have worked in MATLAB, so the CLC command I have written just to clear the screen, and then to clear command is to clear the workspace, then close all. Okay, like another window if you open, then we just simply close it. Okay, and the first part you see here, we have defined the section problem definition. So you can see here I have defined. Yes, any doubt? Yes, Sunita.
No, ma'am.
Okay, so you can see here, are you able to see my MATLAB screen?
Yes, yes.
So this is problem definition. Cost function means this is the objective function. Like we discussed 2 3 examples in earlier, and just now we discussed now the Rosenbrock function. There was objective function. So here the sphere function I have taken. The sphere function. It's just defining the cost function is this sphere function, and you see the sphere function this way. This is the function. Z is equal to sum x raised to power 2. So this has been defined. So simply I'm defining this is the objective function. Okay. Here we call the cost function, and the number of decision variables we have fixed to 5, and the matrix size of the decision variable we have set here like 1, just the matrix we have given. Then the bound, lower bound and upper bound, because the bound is very important. You need to fix the bounds, like we've seen in the example also. Whenever some value was coming out of the bound, we were putting in their bound. So here also minimum and maximum bound we have kept -10 and 10. So this is the first section, problem definition. And next section is, you see, this is the parameters of PSO. Like so many parameters are there. Na? So the first is the number of iteration, maximum iteration. So here I've kept 200. You can put it to 200, 300, whatever you feel like, for depending upon the problem, how much iterations you want to put. And the second is the swarm size, mean the population size. Like in the example, we discussed 8 particles in one swarm. The population size we took 8. Here I have set the 50. Okay, population size 50. And inertia coefficient W I have set to 1. Okay, since this is the damping ratio of inertia weight. Why I have kept the damping version? Because in the other iteration I don't want to keep it 1 for every. It need to reduce this value. That is why I've given it, this damping ratio has been given. Then this C1 value and C2 value, personal acceleration coefficient and the social acceleration coefficient. You see 2 and 2 I have defined. You can set the different values also depending upon your problem. Now third section is the initialization section. So here the particle template, you just initializing the position and the velocity. You see the array you are declaring, and then cost. Okay, cost value, best position, and then the best cost. Okay, and then next you create the population array. Okay, so here we have used the wrap mat, like just this is for the repetition of the array, empty particle and population 1. And the global best dot cost we have set initially to this value infinity. Okay, because we need to find out, we don't know like what would be the global best. Initial value we have set like this, and then we initialize the population members, like the simple for loop we have started. Okay, and now we are going to do this particle generate a random solution. Okay, so we are going to find out this position value, and then we initialize the velocity. Okay, and then evaluation, like here we are going to evaluate, like we did in the example. Now we evaluate the particle position depending upon the cost function. Cost function we just defined x raised to power 2. Okay, so we just value the cost objective fitness value of each and every particle. And then next step is we are going to update, we will update the personal best. Okay, so personal best we will update depending upon, you see, the best position. If it is giving the better fitness value, then we will update the best position, otherwise it will be same. Okay, and then update global best in the same way. Like if there are 50 population size, we are going to find out the best value, and we are going to, like the one which is having the minimum value, we are going to update that with the global best value. Okay, and now next is the this main loop for the PSO. Okay, here we are going, we what we are doing, just we are updating the velocity, the same equation, you see. Like we discussed, there are 3 components: W into particle current position, velocity, inertia, and then the social this cognitive component plus this social component. So we just wrote that, and then we update the position. Okay, in the next statement, and then we evaluate the, you see, the position, the next position, whether it's better than the previous position or not, depending upon the fitness value. And then we update the personal best. If it is better, then we update it, and the same way we update the global best also, like the one which having the minimum value, that would be the global best. And then you see we store the best cost value here, and we display the iteration, you see. And the next part section is the results section. So you can draw the figures, you can make the plots. Okay, and these are the just x and y label, and you put the grid on. So if I run this, you see, run this whole program, so you see this will be the output. So it will draw the, you see, the whole graph also would be drawn. And you see on the left side, the workspace will show the value of each and every parameter value, it will show. Like here you can see best. So you see this, I have opened best cost. So it will just put all the value in the tabular form. Just double click it. And in the same way, this global best, this you can see So all the one that we did mathematically manually, so it will be automated now. Global best, and this cost is also there. So you can just see. So you can see here in the command window, it is showing the best value. Also over here, for each and every iteration, it will show you like 100 iteration we chose. So the best cost it is showing for each and every iteration. So this is the particles. You see the structure for the particle, position and velocity, cost and best. Every value like we did in the form of table now for only 9 particles. So it is showing. You see 50. You see how many particles it is showing. For the 50 particle, it is showing all the value, position value, velocity, cost, and best value. Again, this is the structure. You can open it. Okay. And so this way you can use, like, this is a very simple example I have given to you. You can modify the algorithm also depending upon your need, like how you want to modify, wherever you're getting the best value, best optimal value, whichever you think is better, you can just change, make additions to it.